So in the previous video, we talked about how to balance chemical reactions. That's sort of the focus of this section of Chapter 7. And we talked about when balancing a chemical equation, that number and type of atom on the left-hand side, or the reactant side, has to equal number and type of atom on the right-hand side, or the product side. And so to do that, I kind of advocated for balancing equations using these 4 steps. Making a chart for your product and reactant side as a way to take stock of number and type of atom that you have. Balance those atoms one at a time with coefficients, numbers in front of the species. And then when you add coefficients, make sure you change the chart to update how many of each atom that you have. And then once number and type of atom is the same on both sides, then you are done. So those are 4 steps that you should use when balancing, that I recommend that you use when balancing chemical equations. There are 2 other steps that I recommend you don't have to do, but I find that it makes balancing chemical equations go a little more quickly and a little easier if you do these. One of them I've already mentioned, which is to balance polyatomic ions as a unit. If you have a polyatomic ion on one side of the equation and it stays together on the other side of the equation, then balance it as a unit. The other tip that I highly recommend, and we're going to use in the next example on the next slide, is to balance any free elements last. And what I mean by free elements, I mean if you have a chemical equation where one of the species is just a element by itself, for like example, oxygen or chlorine or carbon, not a compound. Okay? If you tend to balance those last, you seem to not to have to change coefficients as many times to get to the proper coefficients when balancing chemical equations. So let's see what I mean by that by doing another example. So this is actually from your Chapter 7 Canvas worksheet, where part of the problem is you're given this chemical equation in words and you need to write the balanced chemical equation. So I start out by saying gaseous acetylene, C2H2. And since it's gaseous, that's why I put the G there. So gaseous acetylene reacts with, that means add, reacts with oxygen gas. So we've got gas and we have O2. You may be wondering, well, why is it O2 instead of just O? Oxygen, remember, is one of those species that likes to have no fear of ice-cold beer. What that means is that those elements like to be diatomic molecules in their most stable state. We talked about that at the end of Chapter 4, and I think we reviewed it in Chapter 5 as well. So since we have oxygen gas here, oxygen is a diatomic molecule, so O2. So gaseous acetylene reacts with oxygen gas. 2-form, that 2-form means, there's my yield sign. 2-form these 2 products, gaseous carbon dioxide and water. So that's what we get from the words writing this chemical equation. But hopefully you can see now that it, right away that it is not balanced. Number and type of atom on the left does not equal number and type of atom on the right. So we need to go ahead and start balancing. So I do my little charts here. When we start out, we have 2 carbon atoms, we have 2 hydrogen atoms, and we have 2 oxygen atoms. Over here on the right-hand side, we have 1 carbon, we have 2 hydrogens, and we have 2 plus 1 oxygen atoms. So 2 plus 1, that gives me 3 oxygen atoms. Okay, so now we've kind of taken stock in what we have. Let's go ahead and start balancing using those coefficients. So I see that I've got 2 carbons on my left side, only 1 on the right. So I'm going to start by putting a 2 in front of the carbon dioxide. And when I do that, then that changes my carbons and my number of oxygens on the product side. So I now have 2 carbons on my product side. And how many oxygens do I have? I have 2 times 2, or 4, plus 1, so I have 5 oxygen atoms. So that's what I have after putting that 2 in front of the carbon dioxide. So my carbons are balanced. Hey, my hydrogens are balanced, but my oxygens are not balanced. I've got 2 oxygens on my reactant side and 5 on my product side. Not only are they not balanced, I have an even number of oxygens on one side and an odd number on the other side. And so if you come across a situation like that, it's going to be difficult to balance using even numbers. So when you have a situation like this, where you've got an even number and an odd number, using a common factor can be helpful in determining what numbers to use. Between 2 and 5, common factor is 10. So if I put a 5 in front of my oxygens here, how's that going to change things? That's going to give me, erase this, that's going to give me 10 oxygens on my reactant side. So to get 10 oxygens on my product side, I see that I've got oxygen 2 places, right? I've got it here with the carbon dioxide and with the water. So which one do I choose? I mean, because both my carbons and hydrogens both look good. So we're going to have to change both of them. So if I was to put a 2 here, if I was to put a 2 there, I would I would get my eraser, I would have now, have 4 hydrogens, and I would have 2 times 2, and then we have to add another 2, so then I would have 6 oxygens. And you might say, well, that didn't get you very far, Mrs. LaPolla. But no, we can get to 10 oxygens. Remember, we want to get to 10 oxygens. How can we get to 10 oxygens? Well, I need this to be a 10. I need 4 more. What if I was to change that 2 in front of my CO2 coefficient to a 4? So if I put a 4 there, how many oxygens do I have now? I've got 4 times 2, 8, plus 2. Hey, that gives me 10 oxygens. So I'm going to change my table. And you may be saying, oh, but Mrs. LaPolla, you've changed your number of carbons. Yes, that's absolutely true. So I need to change my number of carbons in my chart. I need to change that to a 4. And that's okay, because is there a way I can get 4 carbons on my reactant side? Yep, I can get 4 carbons if I put a 2 out front. And if I do that, then I get my eraser again, and then I change not only my number of carbons, but I have to change my number of hydrogens, both of which are going to be 4, because that 2 goes both to the carbon and to the hydrogen. And hey, look at what we have now. I've got 4 carbons, 4 carbons, 4 hydrogens, 4 hydrogens, 10 oxygens, and 10 oxygens. So this is our balanced chemical equation for this combustion reaction. We'll talk about classifying reactions later on in this chapter. I would say if you could balance an equation like this, you should have no trouble with the equations on the quiz and on the exam that you'll have. I also just wanted to share with you, don't be afraid to go back and change coefficients when doing these problems. We started out with a 2 in front of the carbon dioxide. We had to change it to 4 because of the number of oxygens. As long as you can get number and type of atom on the left equal to number and type of atom on the right by using coefficients, that's how you balance chemical equations. So the last point I want to end with about balanced chemical equations, which we will revisit much more in Chapter 8, is, so why do we have to balance chemical equations aside from the fact that I told you to, and the fact that there needs to be mass conservation in these chemical equations? Why do we care so much about those coefficients? We care about them because we are going to find out later in Chapter 8 that those coefficients relate our favorite unit, the mole. They relate moles of one substance to moles of another substance. So we can essentially use these balanced chemical equations as like recipes to relate moles of reactant to moles of product. But we will revisit that more in Chapter 8. Here's where I'm going to stop this video. In the next video, we're going to start to talk about how to classify types of chemical equations.